Computer. Greetings, Earth and Space Explorers. Welcome to Doc Waller's Earth and Space Report for Friday, March 27, 2026. I'm your host, Bill Waller, an astronomer, science educator, and communicator, coming to you on a cool and clear spring evening here in my hometown of Rockport, Massachusetts. These Earth and Space reports are intended to engage, inform, and inspire people like you who are curious about Earth as a planet, who care about our life-sustaining biosphere, and who wonder about the greater cosmos and all that it has engendered throughout space and time. Video recordings of these reports are archived on the Earth and Space Reports YouTube channel. They are also in regular rotation on the 1623 Studios Community Access Cable Television channel. I'm grateful for the continuing interest and support shown by local science educators and their students, Cape Ann cultural colleagues, cohorts of the Gloucester Area Astronomy Club, myriad Earth and space scientists, educators, and communicators, far-flung friends, family, and other curious folk. Thank you all for your active participation and encouragements. This evening, I'm very pleased to be hosting Dr. Jordan Bretzfelder of Georgia Tech, who will discuss planetary analogs, simulating the solar system in our backyard. Jordan grew up in Washington, D.C. From there, she headed west, earning a B.S. in physics from the University of Southern California, followed by an M.S. and Ph.D. in geology from UCLA. Her PhD dissertation included a study supporting the Curiosity rover's mission operations on Mars, field work in a variety of extreme environments on Earth to better understand Mars, and a wind tunnel investigation to explore wind-driven transport of sand from Venus to Pluto. She recently completed a postdoctoral position at NASA's Marshall Space Flight Center and is currently a postdoctoral fellow at Georgia Tech, continuing her work in extreme environments and contributing to technology development for future missions to the Moon and Mars. In her abstract for this talk, Jordan notes that rocky planetary bodies throughout the solar system have a variety of different surface conditions, from the thick atmospheres of basalt-covered Venus and organic-rich Titan to the ephemeral atmospheres of hyper-volcanic Io and the frozen surface of Pluto. Despite these differences, geological processes and resulting landforms are surprisingly similar on all these worlds. Her work leverages accessible terrestrial analogs, meaning comparable natural environments or systems that are found here on Earth or created in the lab, to better understand these geological processes and their planetary counterparts. The projects she will discuss are conducted in support of ongoing and upcoming planetary exploration missions, including the Mars rovers and the upcoming Dragonfly mission, which is on Titan, right? Okay. As well as other missions in the early stages of development. So let's get going. The Zoom platform is all yours, Jordan.
Great, thank you so much, and thanks for having me. I'm really excited to get to share a little bit about what I've been up to the last several years, I guess. Um, so just making sure everybody can actually see my slides. Perfect. All right, so I'll just get right into it. I'm going to do a really quick overview into wind-driven processes, which is kind of the basis for most of what I do. And then I have a couple different projects I'm going to talk about, and sometimes I'll be talking about, a subcomponent of one of the projects that was most interesting, but lots of different things, and I'm happy to take questions about any of these things at any point. So kind of to do this background introduction on wind-driven processes throughout the solar system, what and who are involved. So the key players are sand and dust, or at least sand and dust size grains of material. And so here's a picture or a GIF of dunes migrating on Mars. And then critically, you need wind to mobilize these grains. So here's a Dust Devil movie that was taken from Mars rover, which I always think it's so cool that we can get things like this from the Mars rover sitting on the surface. We can watch dust devils happening on Mars.
Hmm.
And I'm not going to talk too much about this today. I just want to mention that in addition to the things I will be talking about, there's also a lot of different landforms that result from the erosion of the surface due to sand and wind versus being built up from sand and wind. But I'm just going to focus on the ones that are from the building and moving around of sand. And so to kind of do a little primer into a couple things I'm going to mention later. A dune is essentially a pile of sand that moves in most cases, and there's a stoss or an upwind face, and sand is transported up the stoss to the crest where it builds up and eventually becomes unstable and avalanches down the downwind or lee face. And that process repeats. And every time a dune goes by, it can leave the cross strata or the remnants of that constant avalanching, and that's usually what we see preserved in the rock record where we see it, places like Zion National Park or Bryce Canyon. So there's lots of ways we can learn more about ancient dunes, but I'm mostly going to be talking about modern systems today. And what this looks like in practice, if you're out in the field having a particularly rough day, is sand flying up to face height. So you're just spending all day eating sand while you're out there working, which isn't always that much fun. But it's fun to study active processes until they're too active and in your face. And then little quick terminology things. There's lots and lots of different types of bed forms, which are just the broad terminology for landforms on the surface. And in this case, I'm mostly going to be talking about regular typical types of dunes, primarily star dunes, transverse dunes, which form either under transverse to the wind direction, so perpendicular to the wind direction, or star dunes form under multi-directional winds. And then smaller features that are very common on Mars, but less common on Earth, known as mega ripples and transverse aeolian ridges. So these are things that we don't understand that well because we don't have very many examples of them on Earth, but we see them all the time on Mars. And then just for context, those kind of ripples in the sand that you might see when you go to the beach, those are normal ripples or impact ripples or wind ripples, which are much, much smaller than what I'm mostly going to be talking about today, but they're important to know about. And then where? So, this doesn't just happen on the moon and Mars. We see these features in radarograms from Venus. We see them all over the entire central latitudes of Titan. We see them on Pluto, and in Pluto, they're made of ice. We see them on Io, where they're also potentially made of ice, in addition to basalt, so that volcanic material that Io is covered in. And we see them obviously all over Mars. And most excitingly to me, we see them on places like Comet 67P, and you wouldn't expect a comet to have enough of an atmosphere to generate enough wind to create a ripple in the sand. But sporadically, due to heating of the comet when it gets close to the sun, it seems like enough gas is released when the ice melts and vaporizes to actually generate wind and create ripples there. So we're interested. I'm interested in these things because they really happen all across our solar system and presumably others as well. So they can tell you a lot about what's going on different planetary bodies. And then we have a question of kind of when does this transport happen? Like I just mentioned with Comet 67P, it's sporadic. So I'm going to talk a lot more about that kind of at the end of the talk. And you might be wondering why. And I just mentioned that they're pervasive, but impacts of climate change and desert spreading and the impacts to settlements, et cetera. These are all important things to know and better understand these processes. And then also critically mission operations. And in these cases, it's mostly for our ongoing and upcoming Mars missions, and then our upcoming mission to Titan, where their entire central portion of the moon is covered in dunes and there's sand lots of places. So we need to know when we need to worry about a dust storm, et cetera. And so to get into the first couple things I'm going to talk about, I'm going to be starting with Mars. So here's Mars. And then here's Gale Crater, where the Curiosity rover has been driving around for quite a while now. And for this first section of the talk, I'm mostly going to be talking about data that came from the rover itself, so both the science and engineering cameras on the rover. And then there's an orbital instrument called the High Resolution Imaging Science Experiment that gets us really incredible data of the surface. And we call this HiRISE for short, but you can see the rover in some of the images that this camera gets us from space. So it's really helpful for doing even analysis of pretty small features on the surface. So the first thing I'm going to talk about is a paper that was part of my dissertation, and it's about two different encounters that Curiosity had along its traverse with two different types of bed form. So the first was one of those transverse aeolian ridges I mentioned. It was about 1.5 meters high and about 8 meters wide, and Curiosity was able to drive up and over it no problem, even though they were kind of nervous about sending it up and over a giant pile of sand. All good. Later on, they tried to send the rover through this area called Hidden Valley here, which you can kind of see in panel E, which is full of these mega ripples that I was talking about, which are 20 to 30 centimeters high, so much less dramatic than Dingo Gap, that first location. And the rover very nearly got stuck, and they had to back it up, turn it around, and send it a different way. And so the unlikely outcome of that, where the much smaller features posed a much greater risk to the rover, made us wonder what's different about them and how we can figure out what is safe to send a rover over and what is not for future mission planning. So we went and we looked into it. So to just give quick facts about these two places. Dingo Gap, as I mentioned, was much bigger. It was solitary, just a single bed form, very straight crested, and it was kind of in the opening of this valley mouth, where the Hidden Valley ripples, they fill this entire valley, and they're about 3 to 4 meters apart. And they're pretty sinuous, and there's lots of evidence of interactions, which just to us means that we know that these features at some point in time were migrating, even if they are maybe not migrating right now. And on the note of migrating and changing through time, one of the things we were wondering about the Dingo Gap bed form was why is it positioned where it is and what even really is it? And so we looked for clues that could indicate to us what was going on with the winds in the area around this feature. And we had to do that because the wind sensing instrument on Curiosity was damaged during right after landing. And so we can't really get meaningful direct wind measurements. So we have to use context clues to figure these things out.
Hmm.
And there's a lot of different things going on here, but just to kind of highlight what we were trying to do is we looked for features like these wind ripples with the 10 and 11, or what we call wake features or sand shadows, which are where sand is deposited downwind of an object that blocks its path. And that can give us a lot of information about which way the wind's blowing at a given position, even if we don't have a wind sensor. And what we saw was that essentially there's winds coming from both directions, which kind of explains why this feature is so symmetric versus having an obvious upwind and downwind face. And that kind of explains why this feature is sitting alone in this valley mouth. It's just winds coming from both ways builds up this feature right where it is, potentially. But interestingly, as I mentioned right at the beginning, this cross strata, so cross strata only forms if a feature migrates. And there was some cross strata that's actually visible at the very top of the bed form where the surface of the feature has actually started to erode away and we can see the interior just a little bit. And all that's important about this is that it tells us that this feature didn't just build up as a pile of dust in one place. It actually migrated to where it is, even if it's no longer moving. It also tells us which side of it is upwind or was most recently the upwind side and which side was the downwind side. So the rover in this case drove up the upwind side and then down the downwind side.
Hmm.
Comparing that to Hidden Valley, where there's this whole field of ripples, the rover was approaching the ripples from their downwind side and then would have been driving down the upwind side. And all of this matters because we have done a lot of studies, not me personally, the community has done a lot of studies about the different mechanical properties of the grain packing and sorting on the upwind and downwind faces. And the upwind face, just because it's built up of grains that are transported versus just avalanching down, is actually much more structurally sound, for lack of a better quick way to explain it. And so the fact that the rover was able to get up that much taller pile of material at Dingo Gap was probably because it was driving up the upwind face. So that's kind of one piece of information we can use when we plan future drives, is that if you have to do it, it's most likely safer to do it up the upwind face of the feature if you can.
Hmm.
And then we also looked kind of at as much as we can see of the interior of the features, which in this case, because the rover can't dig, is really just looking at the material that's disturbed by the rover's wheels. So I just want to direct your attention to panel D, which is that wheel track in that first frame versus panel B in this other one. So it's Dingo Gap versus Hidden Valley. And you'll notice that the track at Dingo Gap is a lot more cohesive, the lot preserved a lot better. The wall of the track is kind of holding its shape, which means that the material that makes this up has some sort of interparticle cohesion going on. Whereas at Hidden Valley, that wall failed, the track's not as well preserved. So while it does have some cohesion, it's not quite as cohesive. So this is, strike two for Hidden Valley, and why that drive maybe didn't go as well is that the composition of the interior of those bed forms is just not as sticky as at Dingo Gap. So again, you could do a test run of just one wheel onto the surface and see how the track looks, and then you could maybe decide whether or not it seems safe to drive over.
Hmm.
And then kind of on this note of wheel tracks and kind of using the one thing that the rover changes on the surface of Mars to learn more about what happens on the surface. These drives both happened in 2014, so there's been quite a lot of time since then, and we get repeat images of the same area because the rover is still in the general vicinity. And so we were looking to see what happened to the rover tracks over time, how quickly they were erased. There's been studies that have looked at rover tracks from Spirit and Opportunity, the earlier Mars rovers, and those are generally erased within one Martian year. But in the time captured in these images, and I've gone back and checked at more recent ones too, those tracks are still there. So that's at least 3 Mars years of time, if not more, have elapsed, and the tracks persist. So that tells us that even though there was a giant global dust storm during that time period, those tracks are not being resurfaced, which means that this whole area of Gale Crater is not active in the way that we assumed it was. And these features aren't actively migrating or changing now, but we know that they were once. And that tells us something about how the climate in this area has changed through time in like a relatively short span of time, because these are modern features, but in, on the scale of 10 years, they're not changing, but that means on the scale of hundreds, they most likely were. So this kind of understanding of the details of Mars's more recent climate, when we're not looking at preserved rocks, we're looking at things on the surface. We don't always have the ability to put a marker on the surface and see what happens to it. But in this case, with these rover tracks, it's one of the very few ways we can do that.
Hmm.
And that all that work kind of leads me into the second part of this, which is going to be talking about some field projects I did. The first of which was at these Ibex Dunes in Death Valley National Park, which is the worst place in the world, I think, to try and do work. It's just miserable out there most of the year. Um, but because it's so miserable, it's one of the best examples we have of Mars-like conditions that's relatively accessible. It's much easier to get there than like Antarctica or the high desert in Argentina or Peru. So we use what we have available, and Death Valley is that. And so the whole area we were working in was originally the homeland of the Timbisha Shoshone tribe, and it's currently part of the national park, and was kind of taken via executive order in 1933. But the tribe has been able to reclaim some of the areas within the park, but as of right now, this particular part of the park is still national park land. And so here's kind of a quick overview of the study area. We took a lot of samples, we looked at a lot of different things. I'm gonna just wanted to show you an overview of the variety of different dune types you can have in a relatively small area. So all the ones that look kind of complex and like starfish, those are those star dunes that indicate multiple wind directions. And then the other more straight crested ones, those are those transverse dunes I mentioned briefly. And so we monitored the weather out there for almost 2 years. We took a lot of samples to understand the composition and grain types, et cetera. And then we also did some age dating. And I'm not going to talk about all of that in detail just for the sake of time. But again, I just wanted to show you what the field site looked like. So you might be wondering, like I mentioned, they're remote, but they're accessible. So they are part of a wilderness area of the park. So almost no one ever goes out there, but we can drive there from LA. And I was doing this while I was still at UCLA. So it was a convenient field site. There, up until we published this paper about this about 2 months ago, there was one mention of this site in the like geologic literature, and it was a paragraph in a survey of dunes in the western United States, and so we didn't know a whole lot about it. All of the existing work on the site was about this endemic lizard species called the Mojave fringe-toed lizard, and then truly what we needed was a site that's actually dominated by wind-driven processes or aeolian activity, and Death Valley gives us that because it's the driest place in North America. They typically get less than 5 centimeters of rain a year. There, in this image, we have a ventifact, which is a characteristic erosional pattern in a rock that has only really been impacted by wind from one source for a very long time. And so the abundance of these features in that site tells us for at least hundreds of years, if not more likely thousands, the site has been dominated and mostly altered by aeolian processes. And then lastly, while we were out there doing something unrelated, we noticed that there's quite a lot of features there that look quite a lot like what Curiosity sees on Mars. So the black and white picture is Mars. The other picture with the plant in it is Death Valley. And that's kind of why we wanted to learn more about the site and see whether we could use it to study Mars. So on the note of whether or not a system is active and changing in a given period of time, as I mentioned, those features on Mars were surprisingly inactive. So we were kind of curious about how this site has been evolving in the recent past. So we used historical orbital images to map the dunes through time. And the takeaway from this is that the large dunes, the star dunes, don't really change much at all in this period of time. The small dunes do change in orientation quite a bit over that time, but the large ones are pretty stationary. And just to double check our work, we took a really fancy GPS out there and redid some of the measurements. And you'll see that in the 12 years between a data set my colleague provided and the one we were able to collect, there's quite a lot of points along this particular dune where there were 0 meters of net change in that time. So we've been out there, we've seen that these dunes do have material transported across them constantly, like that video I showed at the very beginning, but it's just back and forth and back and forth. So the sand is kind of just cycling around in the same area rather than having some sort of net motion. And for context, the average dune migration for fields on Earth is somewhere between 10 to 60 meters a year. So 0 meters in 12 years is different than what you might see elsewhere. And then, as I mentioned, Death Valley is very, very dry, which means that there's not a whole lot of vegetation out there, which is great because Mars doesn't have any. So the drier and more arid and less full of life a site is, the more reasonable it is to use it as an analog for Mars. And so there are scrub brushes kind of on the edges of the dune field, but the picture on the bottom just shows that there's no vegetation actually impacting the dunes themselves and altering how they form or evolve. And then I never thought I'd find myself saying the most exciting part of the sand dunes were these ripples, but here we are. These are kind of unusual on Earth, as I mentioned. These ripples, the large mega ripples, those are tens of centimeters high, and there are really very few examples of things like this on Earth, but they're very common on Mars. And those smaller superimposed impact ripples are what you see normally. And just, the fact that these features have co-evolved is unique and interesting and very useful for our studies of Mars. Here's a quick look at the interior of these things. In this case, the structures on the interior of this one just tell us that this feature did migrate at some point in the past, even if it's not actively changing now, because you can see those alternating layers of the different grains.
Mhm.
And that was useful to know so that we know that we have examples of these that migrate, which is what we're lacking on Mars, so that we can learn more about why maybe some of them don't migrate and some of them do. And I'm just going to flip through a bunch of pictures here, but essentially we have examples from the field there showing different types of ripples. And then I'm just going to show you all the different types of ripples we've seen with the rovers. And what I hope you'll notice is that even, in a very small area of Death Valley National Park, we have comparable examples to a lot of these different features. And having them all so close together makes them really easy to study and really easy to compare because they're all in the same environment under the same conditions, but they have all these different morphologies and presentations. So from these kind of geologic, geomorphic, grain scale, all these kinds of analysis, we then wanted to do more of a investigation into how the site changes through time. And so this was part of my first postdoctoral position at NASA Marshall. So we turned to some new technology that they're developing there. So this is the NAC backpack, and that stands for Kinematic Navigation and Cartography Knapsack. And it is a backpack mounted LiDAR unit, which is in this case, a very high resolution 3D scanner. And as the operator, in this case, my former supervisor, walks around an area of interest, it gets really high resolution scans of that whole area. And, we have the technology to do this with drones and stuff, but national parks don't let you fly drones. So you have to find a way to scan very large areas very quickly, instead of just moving a tripod mounted LiDAR around for 3 days at a time. And the other thing, and the reason that they're developing this at all, and NASA cares about this, is because they want to be able to have a device like this help both robotic crews and astronaut crews navigate areas on the moon and Mars that might otherwise be difficult to see. So, like the South Pole of the moon, which is their target, has these really um, dark areas that are permanently in shadow. And so if you can equip the astronaut with a 3D scanner that they can look at in their display, they can now navigate safely where they might not have been able to otherwise. So we were demonstrating the scientific capabilities of what is fundamentally a navigational tool by taking this out to the site. And the downside is that in Earth gravity, the top of that backpack alone weighs about 20 pounds, and total it's maybe a 35-pound, 45-pound unit, depending on how many batteries you have in it. So when you're walking up the steep side of a sand dune, it's not always that much fun. But this would be less of an issue for crews elsewhere. And on the right, we just have an example of what the LiDAR sees versus what we see in the field. And you can see that you actually retain quite a lot of detail with these scans. And briefly, this plot is just meant to show that the scale of the features we're looking at in Death Valley is comparable and meaningfully useful to use to study the ones on Mars, which is what we often are missing on Earth, is features of the same scale and same morphology. So we did a bunch of measurements using the LiDAR data and confirmed that these are actually reasonable for comparison. And then the first of my fancy videos to show you. Here's an example of what the LiDAR data that we were using actually looks like. So that's me standing there for scale. And then this is an area in the northern part of the dune field that we scanned. And you can see all the different ripple textures. You can see the scrub very clearly. In between scans, we could actually see when the scrub bushes were blooming because there's like a difference in the density of the bushes and the total size of them. And you can see the footprints that the operator made as we walked through this area. And what's useful about this is that this whole scan took maybe 40 minutes to do. Whereas if you had a ground-based LiDAR and you had to pick it up and move it in between scans and try and make sure you had overlapping data, that would have been, a whole day to do something like this. And this lets us get a lot of information very quickly. And you can imagine you could retrace your steps on this if you had a little display and know where you were before and know where to go collect your samples, et cetera.
Hmm.
And so as I mentioned, we were kind of trying to understand how the dune field evolves through time. So we were using these LiDAR scans to compare through time to see how they changed. So for example, here we have a scan that was taken on March 4th, and then we repeated the same scan 2 days later. And here, no change is white. Red is addition or deposition of material, and blue is erosion of material. So in those 2 days, there wasn't really much significant change, maybe a little bit of material added to the interdune space. And you'll notice that there's all these ripples in the interdune space that don't really change. But if we compare this to a scan we took 3 months prior in December, you'll notice that there actually is quite a lot of change in that time period. So the dune in the back, we're looking at the downwind face of a dune. The dune migrated about 75 centimeters towards us, net migration that time. And there was a lot of deposition of material in the interdune space, but those ripples still did not move. So much like the ones we're interested in on Mars, even though other things around them are moving, these aren't moving. So this means that we can look inside these ripples and learn more about their interior structure and learn more about how they formed in the first place, to learn more about what's going on Mars and why those don't change and what that means about the climate there. Similarly, we did another example where we scanned 3 months apart, and you can see that the dune in the middle of the image doesn't or changes significantly. It moves about a meter, but there's an area back here that's full of ripples, and that doesn't change at all. So some features are active, some features aren't, and they're all right next to each other, and that's very strange. And then at even finer scales, we can do these scans a day apart. And it was particularly windy between these two scans. So we got a lot of change in that time period. The footprints were erased, etc. And then even like the real benefit of something as quickly doable as what's we could do with the backpack is that even an hour apart, you can repeat the scan. So here's a very, very, very windy day. You can see there's a group of very large ripples in this area. And in the span of an hour and a half, we repeated the same scan, and we can see the ripples move 6 to 10 centimeters just in that time frame. So we have wind data from that time. We have these scans. We can actually meaningfully talk about what it takes to move these ripples at that rate, even though the ones 2 dunes over haven't moved at all in 3 months. So we learn a lot about like the nitty gritty of all these things doing these kinds of scans. And again, it demonstrates the scientific return you can get from a scan that you were already going to do to navigate potentially for a future mission. And then lastly, for this kind of LiDAR themed portion of things, so this same super windy day, we had a different kind of LiDAR that's a frequency modulated continuous wave LiDAR, which is the same LiDAR that they use for self-driving cars. And in this case was literally a self-driving car LiDAR sensor that we took out there. And it gives you Doppler velocities of things it detects in its field of view, which is how it knows whether a car's coming towards you or away from you. And in this case, we actually were trying to figure out if you could determine how fast sand clouds were moving. And you can see it resolves the sand clouds. It tells you they're coming towards you. You can get a speed from that. All of it, which is important for something like sorry, I'm going to advance a slide just so the noise stops. For something like the Titan Dragonfly mission, which is a quadcopter flying around on Titan, understanding whether sandstorms are moving towards you, knowing how fast they're coming, especially if you're a flying type mission, is really important. And they just announced they're sending all those helicopters to Mars in an upcoming mission. So having the technology to understand what the weather conditions are real time when you don't have a human operator there to report on these things and make decisions about how to proceed in a mission is really important. And this slide here just kind of summarizes a little bit about why the Ibex dunes are a good site to study for Mars and the comparison points. And the only real difference between them and Mars is that yes, there's a little bit of vegetation and a little bit of rain, and the mineralogy of the sand grains is different because they're quartz, whereas on Mars they're primarily basalt. But mechanically and as far as physical processes are concerned, everything seems to be happening in about the same way. We see both active and inactive features in both cases. There's almost no human activity in Ibex dunes, and much like Mars, where we basically just have the rovers and that's it. And to the point where we would be out there in December and we'd leave footprints and we'd come back in March and those footprints were still there with no additional footprints added. So like people very rarely go out there. And so it really is a natural lab, and it's a great place to study things as they happen naturally. Which kind of leads me into another mission focused, sand dune focused project I was involved in. Um, this is the Lassie project where we are working on developing this legged robot for planetary exploration. So I'm not sure how loud the audio is for you all, so sorry. But the idea with this kind of rover is to,
as we explore the moon and we explore Mars.
I'm going to pause it. The idea with a robot like this is that rovers are somewhat limited in what they can and can't overcome in topography, etc. But a legged robot has a little bit more versatility as far as what it can and can't explore. You can send it into and back out of a crater reasonably. You can send it over a lot of different types of terrain. And what's unique about Lassie versus just, those Boston Dynamics robots we've seen at all those public demos is that each step that the robot takes acquires a measurement about the surface properties. So there's like a penetrometer in each leg, which gives you information about the tensile strength of the surface and thus whether or not it would be safe to send a heavier duty rover over that surface to then collect with a scientific payload on it to collect more information. So you can send this robot out to scout, where you can then send the more expensive, more robust scientific instruments out, or a crew of astronauts out to go safely explore. So the whole idea of this project is tandem collaboration between robots like this legged robot and other devices. I'm going to jump ahead a little bit.
Alongside the robot.
And I'm going to be quiet for a second so you can hear.
One of the really cool instruments that we are using here in this project is called LiDAR, and it's a LiDAR that's on a backpack. And what the LiDAR is able to provide us is a model of what the surface looks like. It was originally designed to explore how astronauts could be collecting LiDAR on the moon and other planetary bodies. And we can imagine that if an astronaut was wearing the LiDAR backpack and it was walking with its little robot dog, that they could be continuously collecting data together and, again, optimizing how we explore planetary environments.
Yeah. So I hope some of that came through, but I just wanted to highlight that the collaboration between an autonomous team and a crewed mission would probably expedite overall and increase scientific return of different missions, which is why we're doing any of this. And then here is a quick look at inter-robot collaboration. So legged robots pushing a wheeled robot with a very heavy scientific payload on it up a slope that it otherwise wouldn't have been able to get up. And that's what they're studying in this kind of team experiment. So all of this was done at White Sands National Park in New Mexico. And really unique environment, really great if you're really interested in dunes, but also just a great example of the kind of most treacherous terrain you might try to send an autonomous vehicle over, which is why we were out there doing these kinds of studies. Oops. Okay, let's see if this advances the slide. So quick, plug for the LiDAR. With the LiDAR, you can scan an area and have it automatically classify slopes based on a parameter you set and say, okay, don't send the robotic assets up these, it's too steep, but you can try and send it over this way, and then the robot can navigate a safe traverse for itself up that slope. So there's a lot of opportunity for like feedback of information to support mission planning. And then moving on a little bit to kind of a different kind of analog. Meteor Crater is in Arizona. It's kind of near Flagstaff, and it's probably the best preserved impact crater in North America. There are several in Canada, but this one's relatively recent and really stunning. Highly recommend a visit if you're ever out that way. But we were out there as part of a NASA and Lunar and Planetary Institute run field camp that they do out there. And as a planetary geologist who's looking at bodies that are covered in craters, you very rarely get an opportunity to see one in person. So it was really valuable to understand cratering processes. But we were out there in this particular time. Our study was about the properties of crater wall and material on crater walls and how you can use natural processes to infer properties of these materials without actually ever touching them. So on the left is a figure from this paper by Bickel et al. In 2019, and that is the track of a boulder that rolled down the side of a crater wall on the moon. And my favorite story about the Apollo missions is that when they sent them up there, they didn't really know that the surface was going to be supporting the landers. Like they had no idea whether it was 6 inches of this kind of soft seeming granular material or whether it was 6 feet or more. And so they looked at things like this where they're like, okay, well, that boulder rolled down and it left a track about this deep. So that probably means there's something solid under there somewhere. But taking that to a more technical place, you can get a lot of information about the size and presumed density of the boulder, and then learn about, the material it impacted as it rolled down, and what that can tell you about what that's made of and how cohesive it is, etc., as far as choosing safe places to land and safe places to send astronauts. And in a very fortunate turn of events, we had an opportunity to replicate this experiment on Earth, where there was this about 65,000-pound boulder that had eroded so far back, overhanging the trail, that they'd closed part of the trail that people were normally allowed to take around the rim of the crater. And they were going to have it massed waste down the side of the crater wall, which meant they brought an excavator out there and they're going to shove it down. And Dr. Kring said, hold on now, we can do this scientifically if you let us come out before you do it and then watch it happen. So I'm pointing to the boulder back there, and Dr. Kring is the guy standing underneath it, and he's quite tall, just for scale. And so they pushed the boulder off the side of the crater rim, and we had taken a lot of measurements of soil, like physical soil properties on its expected track down. The boulder rolled, and then we went and repeated the measurements. And then we waited for the next satellite pass to acquire an orbital image of the track it left. And then we, we're using all this to feed into, okay, how far off would we have been with our assumptions about the material based on just that orbital image and the boulder information versus what we actually got from the field. And so here's just some more examples. There's quite a large boulder, and you can see here somebody stitched together all these images of the boulder rolling down the hill. And here is just a kind of zoomed in view of that. This is where I was standing, and that's the boulder there. I'm not sure if you can see my mouse, but it was really dramatic, very loud. I think in retrospect, we were all way too close. We probably should have been significantly further away. But you don't often have the opportunity to replicate something like that in a natural system. And you can learn a lot from doing analog studies like this, where you actually artificially create in a natural system the exact process you're interested in. And then I'm gonna kind of hustle here a little bit, but one of the things that was mentioned was that there's also ways to do this in the lab, so you don't always have to go out in nature and look for something that might be comparable. You can generate it yourself. And so again, as I mentioned kind of at the beginning, there's lots of different planetary bodies where we see aeolian sediment transport or wind-driven sediment transport. And in each of these bodies, the atmosphere composition is totally different, the gravity is totally different, the material even that's being transported as sand is different. In some cases, it's different kinds of ices. In some cases, it's complex groups of organics. In some cases, it's just quartz and basalt. And so all these different combinations lead to the same geomorphic expression of sediment transport. And so we want to learn more about how that happens across all these different systems. And the reason we were so interested in doing this is because we have an expression that people use to model this process on Earth, and it's great. But measurements from Mars have told us that that expression isn't actually applicable beyond terrestrial conditions. So we had to come up with a new model that would be applicable outside of terrestrial boundary conditions. And quick little physics aside, the fluid threshold is what I'm going to be talking about. And the fluid threshold is the point at which the upward and forward force from the wind overcomes the downward force of gravity, any interparticle connective forces, and any drag that's holding the particle down. So eventually you keep increasing the wind speed until there's a point where the particle actually saltates. And that's what we were trying to find, because that's what that model is used to predict. And that's what we know was incorrect. And so we use this wind tunnel, and the key takeaway here is that this wind tunnel is open to the atmosphere and operates at ambient Earth pressure. So we had to use analog grains that would still simulate the fundamental physics going on in these other bodies without being able to change the gravity or the atmospheric density in our system. So all we could change was the sediment composition and thus the sediment density. So we use super low density spherical grains. And I'm going to mostly skip over a lot of it's simple math really, but it's just not that interesting. But essentially we were able to find a parameter that basically lets you compare the net buoyancy on a grain in each one of these systems. And by calculating what the buoyancy is in the natural system or the submerged weight, we can then find a particle in the Earth system that has the same net buoyancy. So the physical process is the same, even if the material is different. We also use this parameter called the dimensionless diameter that was from a paper from 2019, but it basically lets us compare grains across a variety of scales meaningfully, because the grains we were using, you'll see in a second, were quite a bit larger than your typical sand grain, but it was the only way to replicate the net effects of buoyancy on the grains. And so We used a couple prefabricated sediments and then a couple custom 3D printed sediments. So 3 different densities of PLA printed plastic spheres. We used hydrophilic beads, which are Orbeez, if anybody remembers those in their dry state. Ball pit balls and table tennis balls. And I recognize that this seems a little silly, but if you calculate out the submerged weight value, et cetera, for all these different things, they actually are identical or within the range of the sand grains on Pluto, Titan, Mars, and Io. So we were able to replicate all of those systems without having a closed vacuum chamber. And a lot of people, when they do this, they do use a vacuum chamber and they use materials like crushed walnut shells. I have a tree nut allergy, so that was never going to work. Or they use microscopic glass beads and have to use laser systems to track the beads. And so the way to do this in the system we had available to us was using these macroscopic spherical grains. And that's the other thing that's really hard to replicate is aeolian sediment is very, very spherical and crushed walnut shells are not. So we were trying to get as many components of the system as realistic as possible with what we had. Quick video. Just gonna skip ahead. So here are the table tennis balls being transported down the tunnel. And then here's a side view of our ball pit balls being transported. So we set up everything on a test bed so that they wouldn't just roll and they'd actually saltate. And then we watched what happened and identified the fluid threshold at the point at which they moved. And so this plot kind of summarizes the existing state of the field. There's all these models, which are the lines. There's measurements from Mars, which are those triangles with the long error bars. And then there's measurements from different wind tunnel studies and our measurements. And the takeaway here is that the models do okay, but not great. If you reparameterize by that buoyancy factor and the dimensionless diameter I mentioned, and then recreate the plot, you can plot a new expression that actually really aligns with both observations from Mars and our wind tunnel data. So this is a very simple expression for a very complex process, but it does seem to actually capture what's going on, which is great. And I was surprised, even after doing all the work, I was kind of shocked that it worked. And then the last thing, which I'll go through pretty quickly, is kind of a different kind of analog. So you can simulate the physical components of a system, you can simulate the environment, you can simulate the chemistry, but if you're sending crews outside of Earth, you also have to understand what happens to human beings when you do that. And so what I participated in was a 28-day simulated lunar surface mission at this facility up on Mauna Loa in Hawaii. And this was a joint NASA and DARPA study, and it was investigating crew psychology. And the mission title actually had the word duress in it. We had no access to the internet aside from our email accounts. We didn't have our phones. We were only allowed freeze-dried or powdered foods that they left up there with us at the beginning of the 28 days. We were scheduled morning to night with like required activities, including geology fieldwork outside or mandatory exercise, a whole bunch of different intellectual tests every day to see how we were doing, all with the goal of trying to understand how a crew learns to work together and what markers there might be for any time there might be a breakdown in crew productivity or efficiency. And it was a crew of 6 people total that I knew nothing about until they picked us up at the airport for training. And we were just up there for a month and had to figure it out. So that was the habitat we were living in the background. We were only allowed outside in these spacesuits, which was about 40 pounds of stuff on you while you're 6,500 feet up a volcano and it's, cold and hot. So it's, there's a lot of stress and strain. And they had us doing a lot of really extensive field work, climbing up and down these lava flows up there. Here's kind of a view inside the habitat. So each of us had, fortunately, our own little bunk at the top. And then there was a kitchen and a hydroponic grow tower. And by the end of week 4, we were each able to have like 6 leaves of lettuce, which was great because we hadn't had anything that wasn't powdered in 4 weeks. So a couple leaves of lettuce felt like a real luxury. Here's the airlock. So we never went outside without the spacesuits on, and you couldn't go out alone. You had to go out with buddies, etc. And you had to observe all these airlock procedures, or they would say, oh, you blew up the habitat, your mission's over because everybody's dead because you messed up the airlock situation. And then here's our solar panels, which is what we were using for power. And then here's a view out of our other window. And there was one day that we saw it snow up on Mauna Kea across the way. So it was a very interesting experience and kind of the only way you would ever, at least for me, ever have firsthand experience of what it might be like on a mission like that, and also gives the researchers a lot of information on how to best handle crew psychology and manage team dynamics and make sure that things are safe, people are comfortable and, happy, and that everything gets done in the way you want it to be done. And so with that, I'll just kind of leave this up, but there's lots of different kinds of analogs and there's lots of different kind of things you can learn from them. And all of them are very important for our kind of progressive goals towards space exploration. Like you need to learn a lot about where you're sending people or robots before you can safely execute that mission. And that's the value of these analogs. So thank you. And I am happy to take questions, etc.
Well, um, that this is a very unique talk in our series, and so I look forward to the questions that our gallery has. So please feel free to unmute, y'all.
I see a question about the robot being sent to Mars. Yeah, ideally the legged robot will eventually make it to Mars. I think, but the current priority is it's Moon first, then Mars. But part of the reason we chose that particular site was looking forward to Mars, because on the lunar surface we expect less of that super loose granular dune type material. It's more very craggy, steep slopes and craters, etc.
Is the reason that specifically because it's better than the wheels? I mean, specifically why?
It's it has the capacity to go places where a wheeled robot would not be able to, but there's also the more complex the system and the more complex the mobility components of a system, the more likely there are points for failure. So that's another benefit of kind of having it be a team of them and working in tandem, is that you can kind of supplement any issues you might have with alternate ones. But also, just due to the design of the robots, they are somewhat limited in the weight they can carry and still navigate effectively. So they're more scouting and getting information that can then be used to inform where you send a wheeled rover that has the more typical payload on it.
I think maybe if you could stop sharing your
Oh yeah,
screen.
sorry.
Well, you may have to share again. Um, so what strikes me with these Mars analogs and Mars itself is that the atmospheric pressure on the surface of Mars is 100 times less than here on Earth.
Mhm.
And that corresponds to the density of the air being 100 times less. And yet you see very similar behaviors in the dune making. You mentioned rates of dunes moving around, and you said they were comparable.
Yeah. So that was kind of what was shocking about that kind of equation not being applicable, because from all the observations we'd made so far, like we know the dunes are migrating, we know they change, we know that the grains in the dunes are approximately the same sand size grains we have here on Earth. We know
Hmm.
what the composition is. So, what is the difference? And it is the overall dynamics of the system in that much lower density atmosphere, with also a much lower gravity on the planet overall, that leads to the boundary at which a grain will move is different than it is on Earth.
Hmm.
And a other significant difference between Mars and Earth is that once you have one grain move on Earth, it can generate a bit of a splash of other grains when it impacts, and that can kind of carry on the process of grains moving a bit. But the wind speed at which that splash process stops working is pretty close to the wind speed that it took to move the initial grain. But on Mars, that splash process is efficient down to 80% less wind than it took to move the first grain. So you need a gust of wind to move one grain, but once that one's moved, you need much less wind to continue grains moving.
Mm.
And so, like, yeah, just the overall dynamics of the system are very different, which you would expect given that there's different conditions, but they're not always different in ways that are easily predictable. Like you kind of have to see the system and replicate the system to understand the differences.
Yeah.
And you got the wind devils that I'm
Mhm.
sure kick up grain all the time, all the
Mhm.
time.
Mhm.
Yeah.
And yeah, the rover team still actively monitors for dust devils because, again, they're trying to learn as much as they can about the climate, even though the wind sensor doesn't really operate as anticipated. And those are very informative for active processes because we can watch them happen.
So you're the expert on this. The movie, what was it, Mars? Is that what it was called? Um,
Oh, the Martian?
The Martian, thank you. It starts with this big storm.
Hmm.
and it just blows all their infrastructure down.
Hmm.
Uh, is that not feasible, or is it feasible?
Um, that's actually the only component of the movie that isn't physically feasible. Like the dust storm itself and the scale of the dust storm. I think there's two dust storms that are part of that film. Both of those are reasonable. It's just the wind's strength is not enough to knock over that kind of material, assuming it was really, supported the way it was. And even the author Andy Weir was like aware of that. He
Mhm.
had Jim Green, the at the time chief scientist of NASA, consult, and so he needed it for a plot device, but he knew that it wasn't exactly physically possible.
Thank you. Oh yeah, I'm 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 having somebody trying to get them to unmute, but I can't unmute them.
I was caught in a snowstorm on Mauna Kea, so snow definitely happens there.
Mhm. How long were you stuck up there?
Well, I went to help out Meacham, who's a director up there.
Mhm.
She was going to use the 86-inch till the moon rose at 1, and then it was going to be mine all night.
Mhm.
And late afternoon, we got there early, helped us set up the nitrogen tanks. But an hour later, some guy comes in covered in snow in a parka and says we have to evacuate the mountain. We had
Wow.
no idea. We go outside and there's a major blizzard. So it happens.
That's really wild. I mean, we saw kind of a dusting, nothing like that, but that's really cool.
Hmm. Patty, do you have any questions having to do with uh, sandy places?
I'm just stunned. It's going to sound weird because I'm not my brother, who's an astronomy geek.
Hmm.
Um, I learn as I go, whether it's a GAC meeting or Bill's meetings. But every once in a while, we'll have a presentation on something that people study that. It would never occur to me to have that being studied. And it was fascinating. Thank you
Thank
so
you.
much for that. Wow.
It's a real example of curiosity-driven science.
Yes, yes. And it was just brilliant. Thank you so much for that.
Yeah, thanks. And I kind of stumbled backwards into this myself, so it was not something that I, from a child, was like really passionate about sand. But
Woohoo! I was going to say,
we we find things that are, need more investigation than we just do it, I guess. But yeah, I'm glad you enjoyed it.
very, very much
That's
so.
very nice. Would this be applicable, I suppose, to Titan as well, since that has sand dunes?
Hmm. Yeah, we don't know quite as much about Titan sand dunes, but there's a lot of people who do very interesting wind tunnel studies in vacuum chambers that are pumped up to Titan's pressure.
Mm.
And they think the grains on Titan are actually just like clumps of organic molecules versus being made of rock grains
Wow.
necessarily. And so the interparticle kind of stickiness of those grains might be very, very different than we're used to seeing. So when Dragonfly lands and gets a look, I'm super excited to find out what's going on.
Hmm. Do you envision future analog missions to Antarctica to see how I guess it's snow transports there?
Yeah, there are actually some snow bed forms and I guess ice grain bed forms in kind of the center of the continent. And I know somebody who works on observing those remotely. The job I'm in now, I actually was supposed to have been in Antarctica this past winter to study stratigraphy around a ice-covered lake as an analog for early Mars, where there was liquid water under these ice covers, most likely, just due to changes in NSF's budget. We weren't able to go this season. Hopefully, we get to go in the future.
Mm.
But there's lots of different kinds of systems you can replicate in Antarctica, and it's a really unique environment that obviously is one of the few where we don't have to worry about people or very many animals impacting the things happening. So hopefully, we get to go.
Mm. Well, this was as I said, in this series, this is the 71st episode.
Mhm.
Um, this was truly unique, and I kind of regret that we didn't have some of these other folks who were talking about in a prior episode uh, having to do with creating new habitats off planet,
Mhm,
and you even got into that a little bit.
mhm.
How did you fare?
Oh, I thought it was, I was pleasantly surprised that it wasn't so bad. We did actually, unfortunately, have a bit of a mix up with the food that they left us up there from the beginning. And due to the structure of the communications, because of how limited they wanted it to be, it was like not properly conveyed how dire the situation was until our exit interviews. And while I recognize this was a position I put myself in by volunteering, we were actually starving for that whole time. Um, in the 28-day mission, one participant lost like 16 pounds
Wow.
because we were doing this like really very active, either outdoor activity or required exercise and like not having the caloric balance out. So aside from that, it was great. And I'm still very good friends with everybody I met up there. And I feel very fortunate to have had the experience.
Yeah. Well, may you have many more uh, missions like that, maybe with a little more caloric content.
Yeah, just like a say in the meal plan next time. Otherwise, send me back.
All right. Any other thoughts by anybody?
Great presentation. Thank you.
Thank you.
Absolutely.
So,
One image that just popped into my head, and I'm sure it has nothing to do with stuff you study, is a couple of years ago, and I'm sure it happens more often than I hear about, is sands from the Sahara
Mm,
flowing completely across the ocean and messing with us here.
mhm,
And see the haze in the air.
mhm.
How does that happen?
It's, it gets lofted high enough and then it's just caught in, the very strong winds higher in the atmosphere and it makes it all the way over. I think my favorite picture of that is there's a couple images of people skiing in the Alps with the snow covered in that really golden Sahara sand because it blew across
Wow.
the Mediterranean.
Yeah.
So yeah, you know, global systems like that, we are still learning a lot about how important they are to the entire planet's climate.
Absolutely.
And we want to know the same things about Mars, and we're trying, we learn more every day.
Fantastic.
and
It's bad for your skis.
yeah.
Yeah.
And in your abstract, you mentioned that there's transfer of sand from Venus to Pluto.
Oh, that may have been phrased poorly. I just meant that on planetary bodies between Venus all the way out to Pluto, like a bunch
Oh,
of different planets, that same process happens.
well, good.
Yeah.
Thank
I
you
was
for
just happy
clearing
to
that
hear
up.
people are still talking about Pluto. Poor
Yeah.
thing.
It must be a strong solar wind to do that.
Yes, there's always that.
Must be.
Mhm.
All right. Well,
Excellent.
I want to thank you again, Jordan. This was really eye-opening.
Thanks so much for having me. It was really lovely meeting all of you as well.
Have a great
Okay.
evening.
Thanks.
Take good care.
Thanks.
Bye, all.
Bye, bye, gang. Thanks.